Is it on now? Ah, okay. So the fourth-year PhD under the supervision of Uri, but today we'll be talking about a project we started with Jeremie about the dynamical history of Kappa-Cygnid and August Draconid's meteoroids. To start with a little background, or what inspired us to look at these showers, was their similarity in radiance for the meteors, while having different orbits of their meteoroid streams. So we wondered if there's any dynamical relation between these meteoroid streams, and if so, how did they separate into those two radiants, or if the connection is purely coincidental. Uh, the the inspiration came after hearing a talk from Jiří Borovička. So afterwards, we wrote him an email and asked for a few representative examples of those orbits, and we received one meteor of Kappa-Cygnid and one August Draconid to simulate. And we can see them on the graph here. The shorter orbit belonging to the August Draconid, and the longer to the Kappa-Cygnid. To perform our simulations or our study, we used the methods of n-body simulations using the software package called REBOUND by Hannah Rain. And it's a very versatile package for n-body simulations containing many integrators, more than 10. It also contains several collision and gravity solvers for use in various parts of astrophysics. And there's also associated package called REBOUND X by Tamayo and colleagues, which contains many non-gravitational forces and effects, some of which we have also used. So, about our simulation design, we performed a few different simulations, all of them containing 10,000 clones of the nominal orbits. We used 4 different size bins, about which I will be talking in the next slide. And for all those 4 size bins, they were doubled to get 2 sets of simulations, which are different due to their clone generation. In one of the sets, we used 1 sigma errors for generating the clones of nominal orbit, and in the second set, 3 sigma errors. So that gives us 8 simulations in total, which were then integrated for 1,000 years, which is about double the Lyapunov times of the meteoroids, using the IS-15 integrator in REBOUND, which is a high precision 15th order integrator with adaptive time step, which is great for many astrophysical problems, mainly when dealing with close encounter with planets, which, as we will see, will be very useful. All of those simulations were performed at the Clara High Performance Computing Cluster at our university. And all of them were, so there were 8 simulations for Kappa-Cygnids, and 2 times, because another 8 simulations for August Draconids were needed as well. Getting back to the size bins, as we're dealing with small meteoroids, we have to take into account not only the gravitational force, but also non-gravitational force. In this case, the radiation forces, namely the Poynting-Robertson drag and the radiation pressure from the sun, which are both dependent on the beta parameter, which corresponds to the particle size. These radiation forces were included in the aforementioned REBOUND X package. And here we can see the 4 size bins, which were used in the simulations, which corresponds roughly to 10 centimeters in particle size down to 10 micrometers. Now getting to the results. And as we heard in the previous presentation, the phase space is quite chaotic, which is quite evident in the August Draconid simulation. Well, a bit less evident in the Kappa-Cygnid, but still. And the source of this chaos and all these particles is mainly Jupiter and close encounters with other planets, but the Jupiter is the main perturber. For the Kappa-Cygnids, most of the perturbance happened during the first 50 years of the simulation, but not for a significant part of the particles. Looking at the first size bin, in the first 50 years, 1600, not even 1600 particles had a close encounter with the planet, mainly Jupiter. While for the August Draconids, the first 50 years were the most stable part of the simulations. And then in the next 50 years and beyond, the close encounters started. And yeah, in the second 50 years of the simulations, almost all of the particles had a close encounter with the planet. Now, taking a closer look at or detailed look at the first 100 years, we can see that the Kappa-Cygnids start getting perturbed quite soon. And after the 50 years, also the August Draconids. To better understand the unperturbed behavior, we removed all the particles which had some kind of close encounter with the planet, and these are shown in these. So yeah, we can see that for the August Draconids, not a lot of them are left. But another thing we can see that the orbits or the particles are still not getting closer together. So that's one of the first clues that there is not a real dynamical connection between them. Certainly not on this time frame of 1,000 years. Next, we can move on to semi-meteoric eccentricity, which is also plagued by the chaos. But out of the chaos, in the Kappa-Cygnid simulations, we can see a bunching or compacting around the 3-2 motion resonance with Jupiter, which is a bit different from the published results, which suggest a different mean motion resonance, and we're not quite sure at the moment why that happens. Once again, the detailed look at the first 100 years for one of the bins. We can see how they move around. And right about now, yeah, the chaos kicks in for the August Draconids. Yes. So once again, we removed all of those particles which had close encounters. We can see the 3-2 resonance with Jupiter getting stable there. And also, after removing those particles, we can see a quasi-mechanism with the August Draconids, which raises the eccentricity while lowering the inclination, which we'll see later. All of those can also be seen on these heat maps. And we can see quite a stable evolution around the 3-2 resonance with Jupiter for the Kappa-Cygnids. And for the August Draconids, we can see the chaos that kicks in after those first 50 or 60 years, where the space gets thinner with particles, also in the eccentricity space. Now for the perihelion distance and inclination. Once again, we can see the chaos kicking in quite soon, mainly for the August Draconids, not so much for the Kappa-Cygnid's, but still. Taking a closer look at the first 100 years. And yes, soon the chaos will kick in here. Oh, yeah, it's there. And after removing the particles, which experience the close encounter, we can also see the quasi mechanism for the August Draconids. And the inclination is dropping from the initial inclination of about 35 degrees down to roughly 10 degrees in 1,000 years. So, to summarize our findings for now, we are mostly sure that these are probably not dynamically connected, and that the similarity in their radiance is coincidental. We have seen that both of the streams are affected by Jupiter encounters mainly. There were also some encounters with Earth and Venus, but the Jupiter is the main perturber. The Kappa-Cygnid's appeared quite stable in the 3-2 Jupiter mean motion resonance, and the August Draconids seem to be caught in a quasi mechanism with a quite chaotic evolution. Another step we want to take is to estimate the ages of these streams. So that's the work for the following days, weeks, and months. Thank you very much.
Thank you very much, Filip. Okay.
Okay, thank you. Yeah, I know what a resonance is. Can you quickly remind me of the quasi mechanism?
It's a mechanism in which the particle, the simulated particle or real particle, exchanges its inclination with eccentricity. I think Aisha was talking about it in her talk, or someone else? Yeah, Aisha. And yeah, so I'm not really sure at the moment at the real details, but yeah, as we've seen, the particles were exchanging their eccentricity for inclination, and it should be a cycle on longer time frames.
Okay, thank you. We have time for more questions. There is nothing online. I don't know if we have here any other question in the room. Okay, so then we can thank Filip again. And we continue with the